Hello and good morning or good afternoon, depending on where you're connecting from or what time you watch this. Welcome to another edition of the Relatorium Seminar. We're very happy today to host, one of our own. I mean, Tim Hosgood is really an honorary member. He runs the Topos operations at Oxford, and he's going to talk to us about why use categorical methods for modeling, and the context will be epidemiology. So I'm really excited about that. Tim,
Cool.
take it away.
Great. Thanks, Ted. And yeah, feel free to jump in with questions at any point. It's nice to have this as a bit more of a chat type thing. Let me share my screen and bring up my slides quickly. So yeah, I'm going to be talking today. It's sort of a repeat talk, but not out of laziness, more because I just find this talk a very exciting one to give. So I talked about this here in Oxford in our local seminar about 4 or 5 months ago. But actually, it was about sort of like current ongoing work at the time, and this work is still ongoing and it's changed a little bit. So it's nice to be able to revisit this and talk about some updates. I will preamble this by saying that I've been a little bit sick over the last couple of days, so my head isn't at full compos mentis yet. So if I jump around a little bit, I'm sorry. Please do interrupt if anything gets a bit too confusingly worded. But yeah, so what I'm really interested to talk about today is this idea of categorical modeling. I want to talk about what it means, why we care about it, why we're thinking about it at Topos, and how it fits into some of the other stuff we're talking about. So really thankful for getting the chance to speak here, and I'm really excited to sort of hear what people are thinking about this kind of stuff. So I want to start by talking about, what we're going to do today. Um, so um, here's the context. So in January of this year, 2026, we are in indeed 2026. I, along with a bunch of people from APEX, which is the Center for Analysis and Prediction of Pandemic Expansion, which is an NSF-funded organization led by Nina Pfeffman, and then Mary Lou Zeman, who's amongst other things at the American Institute of Mathematics. We organized a workshop held in Pasadena on formal scientific modeling, a case study in global health. So this was a convening of some people from Topos, some people outside of Topos, some people from Apex, and some people from AIM, and all of these different, and a bunch of external people who have nothing to do with any of those groups, sort of by membership. And some of us were biologists, some of us were epidemiologists. There were a lot of multidisciplinary modeler scientists, and there were some category theorists and some mathematicians. And the aim was to sort of figure out what are the problems faced in formal scientific modeling, specifically in the context of global health. When and when not can category theory kind of help with that? What sort of things do we find would be interesting things to work on together? Where do we find we have common problems that could be interesting to resolve? So it was a week long. There's a website on it. I'll share these slides afterwards. These are all links you can click on. It was a week long. It was really good. We had some really cool talks, and I learned a lot from it. And that workshop in January is sort of what sparked what I'm going to be talking about today. So here are the sort of like, I don't want to call them arguments, and theses is a very fancy sounding word, but here are the sort of things I've started to believe in some sense that I'd like to talk about today. And these were some of the things that came up as a result of this workshop we had. So the first one is the idea that whatever a formal categorical model is, building one is useful and complex. So this is the first thing that I'm hoping to sort of demonstrate today, that has its uses, but it's not very easy to do in certain ways. And the other thing is that building a formal categorical model is made considerably easier if you have the right tools. And these tools are both sort of mathematical, they're also sort of external to mathematics, and they are tools in the sense of like software. So these are the two kind of things I'm trying to sort of express today, is that this idea of formal categorical modeling is useful but difficult, but there are ways in which we can make it easier. So these are the two things to sort of keep in mind. And so these are some of the questions that were raised during this workshop where sort of some of us from Topos came along with these sentiments, these theses, we're expressing them. These are some of the questions we sort of pin down as concrete things to try to answer. And again, these are some of the ones I'm going to try to address today. So the first one is, how can this formal categorical modeling, which again, I've yet to really define, but we will get to, how can this help people better understand scientific models outside their expertise? So one way of understanding this question is, if you want to do public health, then, that it's not that you just have a type of modeler called a public health modeler who does all of the models for all of public health and they cover every aspect, right? Because if you want a good public health model, you need to understand lots of different levels of what this model is. For example, there's the very much like interbiology level, right? There's a cell level. When we administer a vaccine, how does it act within the body? How does this work as a biological human as an individual? But then there's the sort of more one level up kind of ecological level, maybe, where you look at the ways that human beings interact with one another, which can be a carrier or a spread of disease. And then all of this happens to, be situated in the context of reality, right? So we need to worry about sort of economic factors. If we want to institute a stay-at-home policy, is that tenable? Is that sustainable? Will there be other factors driving people? And there's all of these different aspects of the model that require different expertise and different modeling paradigms. So how, when we're building these large-scale models, can we help people from these different areas to express what their models are really saying? And again, we all of these things we'll see some more examples of to sort of clarify them. But something else that's key here is sort of outside their expertise doesn't just mean within scientists, right? This also means if, to use some lazy phrase, like a general member of the public is looking at a scientific model, how can they get information from this, right? If a policymaker is looking at it, how can they get information from this model? How can we help to express information? The second question is sort of like something that we say quite a lot, we meaning categorical modeling people, is we say something like categorical modeling makes your assumptions explicit. And I really want to try to understand in a worked example what we mean when we say that. And then this third question is, how can we allow for informal looking diagrams to convey precise quantitative information? And again, we're going to see this through a worked example. And then sort of, if I have time at the end, I want to talk about these two bonus questions, which is sort of like, what does it look like to have software that supports this process? And so one type of software that supports this is Cat Collab, some of the software we're working on at Topos. So then this fifth question is sort of like, what does it look like to add new functionality to this software? Like, is that a research problem? Is that a software problem? Is that something else entirely? So this is sort of the things I'm going to be trying to address through a worked example. So here is the worked example we're going to be doing today. Today is sort of, sort of collaborative as much as it can be exercise in building a model for ourselves. So there is a paper by Mary Zeman and Nina Pfeffman and other authors on an immuno-epidemiological model for transient immune protection. And I am not a biologist, so let me be very front about that. So as far as I can understand, it's a paper about a certain kind of respiratory infection that's caused by a virus and understanding models of these. So this is a paper that came up and we discussed during the workshop. And the model, like sort of what is the model? If you open up this paper and you'll look at it, you'll find that there's sort of three main bits that define what the model is. I mean, the whole paper is a paper. You can argue everything in the paper is the model, but there's three bits I'd like to extract. There is a formal system of ordinary differential equations. There are these very rigorous, mathematically defined equations, which are studied by analysts. We can computer simulate them. We can do lots of things. We can try to solve them, draw graphs, all this kind of stuff. A second thing that appears is a parameter table. And I'm going to show screenshots of all of these in a sec, don't worry. Second thing that shows is a parameter table. And as we'll see, this kind of gives a little bit of context to the ODEs and tries to tie them into their real world interpretation. And then the third thing is an informal diagram. So these are listed sort of in order of pure mathematicsness to less pure mathematicsness. And then there's this third part is this informal diagram, and I'm really interested in that as well. So let's have a look. So here is the system of ordinary differential equations from their paper. They just give you this. And this is something you could give to, a mathematician who does differential equations, and they need not know anything about respiratory viruses or lungs or anything at all. They just know functions and real analysis and some differential geometry maybe. And they could study this. They could find its stable points. They could simulate it. They could do lots of interesting stuff. But what makes this a model is not just this system of ODEs, right? It's sort of what are we thinking of this system of ODEs as meaning? How do we interpret this? What do we understand it as? So this is where the parameter table comes in. So here, first of all, they give you a bunch of experimental values and units. They say, this variable that was just called P, you should interpret that as the viral production rate. It has some meaning. We are telling you that P isn't just a random real number, it's a viral production rate. And here's a value. Maybe it's a lab tested value or a hypothesized value or a measured value or something like this. So this parameter table is the bit that sort of interfaces between the pure mathematical model and the way we're meant to be thinking about it and what it means. Yes,
Tim,
Ted.
can I make a little suggestion here?
Sure.
Perhaps because you mentioned, obviously, the previous slide is an example of a general system of nonlinear differential equations, and
Mm,
that can be studied on their own for a variety of reasons with variety of techniques. I like to think of the parameter values and
mm,
ranges as restricting, in some sense, the domain so that we could enhance our ability to draw conclusions from this. Because, in some sense, one of the things we have learned over the years by studying nonlinear
mm.
differential equations is that, they're largely intractable in general,
Yes,
right? There's not that
exactly.
much. The things you can say precisely are very vague in general.
Yeah,
So, yeah.
exactly. Like even on like a very like down to earth level, something that's useful, if I read this table and I hear that I don't know, that one of these things is maximum cell capacity of the target tissue about halfway down here, that probably tells me that that number should never be negative because I don't really know what a negative capacity means. So these parameter tables help me to understand sort of which bits I'm interested in fixing, which bits I'm interested in varying, which bits I'm interested in monitoring, and any sort of bounds that might be on them. Yeah.
Right. And in particular, what I have in mind is the problem of non-uniqueness, which plagues
Mhm.
often nonlinear dynamical systems.
Yep.
And to some degree, I mean, not that this necessarily goes away, it might interestingly still stay, but
Mm.
we're homing in to the types of behavior and solutions that actually matter in this context, because it's the context
Yeah.
that we care about, not the general
Yeah.
framework, right? The reality is the context, not the
Yeah.
framework.
Exactly. Yeah, and as you'll see, one of the main focuses here, maybe surprisingly speaking as a mathematician, is that I'm actually not super interested in this talk in talking about the solutions to these equations or like how we simulate them or whatever. Like that's a whole thing. It's a really cool story, but that's not the story I'm going to tell today. I'm really interested in sort of how to do this tying of what these equations are saying to what they're kind of meaning in reality. So yeah, so there's this parameter table, and then the third bit, which is my favorite bit of the paper, and this is the bit that led to all of this work, is this diagram they give. So this is their informal representation of their model. So the thing that I find super interesting about this diagram is just a picture, right? Like in some sense, it's purely pictorial. I've spoken to the authors, and I was like, oh, does the fact that the interferons are in a little cloud and the antibodies are in a spiky thing mean something formal? And they're like, no, it's just suggestive, right? Like the antibodies are spiky guys, and there's some sense in which this model is just meant to be helpful in sort of understanding how they have laid out this model, the way they've sort of constructed it. But the thing that's very interesting to me is if you talk to one of the authors of this paper, but more generally like a domain specialist who draws these kind of models, from looking at this picture, they can reproduce this system of ODEs pretty faithfully, right? They might go, oh, I'm actually not too sure when the author here is talking about the virus antibody interaction, which of these common types of models they might be using. But they would not be surprised to see this table of ODEs having looked at this diagram. And that's the part that I found super captivating.
Tim,
Uh,
I wonder, are you familiar, have you heard of the work of John Sterman in business dynamics? He's one of the, yeah, yeah,
yeah,
yeah. He's one of the guys who basically, take systems dynamics and apply them to policy
yeah,
making in the business world and so on.
yeah,
And they do very similar things. They call them, uh, uh, clo what do they call them? Causal loop networks, diagrams or
exactly.
whatever.
Yes,
And yeah, yeah. And in fact, so the polarities, I see I think maybe you're going to tell us about it, but whether the
yeah.
end of the arrow is a pointy or a dash.
Yeah, a bar, and you can already see this, and like there's some dashed arrows and some fast arrows, and there's obviously something meaning here. So yeah, a lot of this work, the reason that this diagram interests me so much is previously at Topos, we've been doing a lot of work with these causal loop diagrams, with these stock flow diagrams, with these sort of graphical diagrams and understanding semantics for them, ODE semantics. So I'll talk a bit about this. But yeah, definitely this work is all super related. But for me, the really captivating part was, you know, the fact that some expert can look at this diagram and largely recreate the ODEs from looking at this is very interesting because it means they have some knowledge. When they look at this thing, they can contextualize it and really understand it. Is there a way that we can sort of help them get that knowledge onto paper? It's something I think you experience a lot once you start to, you do a master's, maybe you do a PhD, you start to do research, is it's very difficult to sort of convey knowledge that is just stuff you've kind of absorbed passively over 10 years or actively, but like there's a certain kind of knowledge transfer that's very difficult to put down on paper. And that is generally the thing that we call like expertise, or sort of like intuition or something like this. So I'm very interested in trying to find ways to express this sort of like amassed knowledge that we might have. So what I want to be doing today, the thing we're going to be doing is going, okay, is there a way we can go backwards now? We take this diagram really seriously and then see how close we can get to recovering this system of ODEs. So that's sort of like the group exercise we're going to be doing today. And I say group because I might try to solicit some participation. But the way this exercise kind of works and the way this was working when I was speaking with Nina and Mary Lou was, they've explained something to me. And I think a good way to communicate knowledge to one another is, then the other person tries to explain it back. They go, oh, okay, here's what I've heard. And when you explain something back, it's a good method, I think, of sort of communication because the person, the expert in this scenario can go, okay, no, I think there is where you've got something wrong. I think when you explain this, you're making this simplification, or yes, that's true in this case, but generally, you shouldn't have that hypothesis. There's a special thing here you've noticed. So this is sort of what we mean by, we often talk about the phrase interrogable models, models that can be interrogated. So I want to be clear with the framing just before I start on this exercise. The point here is not to take a model in immunovirology and go, look, we can throw mathematics at this and now mathematicians understand it. The aim here is to be sort of entirely the opposite, where I, as a mathematician, can start to build a model which I show back to the domain specialist and go, how do you feel about this? Am I understanding these things correctly? Am I getting at the right ideas here? Can you see the assumptions I've made? So that's really the way this thing is going. This isn't sort of a like mathematical hegemony activity. This really is a sort of trying to explain something back so that people can point at it and go yes or no. So that's the sort of exercise we're going to be doing now. So I'm gonna get started on that. And what I want to do, so I've brought up here the ODEs on the right and this diagram on the left, and I've grayed out everything I'm not interested in. So on the left here, I've drawn a little purple circle around a part of this diagram. And on the right, I've drawn some squares around some of the terms in the ODEs. So, as a mathematician, maybe I've seen these things called Petri nets and stock flow diagrams, and I've heard of mass action semantics. There's something that makes me guess that that purple circle on the left corresponds to these three terms on the right, the terms with a VT in them, basically. So, I don't really know anything about biology, but it seems feasible to me that like a virus and a host organism, the target cells, combine in some way and make some infected cells. That sounds sensible. So that's what my understanding is. So let me now try to write that down in such a way that I can show it to a biologist and go, is this right? Am I understanding what this model says correctly? So here's the sort of language we're going to be building. I'm going to be building these diagrams, and along the way, I'm going to go, here's how you can sort of recover ODEs from them. Okay, and then I can build a big diagram, look at the ODEs that are generated by this diagram, and if they match the one in the original thing, then maybe my diagram is a good one. Maybe my diagram has some meaning, and maybe I will end up rediscovering exactly the same diagram that they've drawn. The spoiler is I won't. It will be different, and the ways in which it's different are interesting. That's the sort of claim here. So let's come up with the first rule of this game we're going to play, of this diagrammatic notation. So I'm going to draw boxes, and they're going to have arrows between them, just like the original diagram. but I'm going to do something different. I'm going to have two types of boxes. One of the boxes are going to have these, you can't tell the difference too well, but one of them has rounded corners and they're pale blue. The other ones have square corners and they're dark teal, I guess. And there are some arrows. And what are the rules from arrows? They always have to go from one type of box to another. They can't ever go from the same type to the same type. So if I introduce some terminology here, I would call these things, these light ones, I would call places,
Mhm.
for example, and I'd call these dark green ones transitions. So this is a specific choice of terminology.
Yeah, I was
Yeah.
going to say this is inspired surely from Petri nets and the idea, like in chemical
Yeah.
modeling of chemical reactions,
Yeah.
the
So
species and the reactions and so on.
exactly. The kinds of diagrams I'm about to build sit nicely inside a sort of subfamily of Petri nets. So there are a few different ways I could think of these. I could think of these as multi-Ariestock flows. I could think of them as multi-categories. There are a bunch of different things, but I'm going to use Petri net terminology. So it doesn't matter if you've never heard of Petri nets before, because we're going to be explaining part of them. But yeah, definitely here, secretly in my mind, I know something about Petri nets. So I'm going, this seems to be a convenient language here. So I have this part of the model has three places and one transition. And you can see that these three places here are related by this one transition. So what does this mean? It means there's some process that I'm calling infection. I'm saying there is a process called infection, and it sort of takes in target cells and a virus, and it gives out infected cells. So to me, this is sort of like I'm stating that like this is one process. It makes sense to draw a circle around something and go, this is a thing, right? And I could go into a very long discussion about what it means to like draw a circle around something and point at it and give it a name. And that's super interesting, but I'm trying not to get off topic. But so here's the rules of how I'm going to interpret this sort of diagram. I'm going to say every single place. So I put here their like name with a capital letter at the beginning. So T, I, and V. Every single place corresponds to some quantity that I want to track. So the number of target cells, the number of viruses, the number of infected cells. Every time I have a transition, I'm going to update my big system of ordinary differential equations in a certain way. What am I going to do? I'm going to look at every place that goes into the transition. So here it's target cells and virus. And for the ordinary differential equations corresponding to those variables, I'm going to, I think here I've got my pluses, my
I
minuses
was,
the wrong way around.
yeah,
Yeah,
that's what I
that
was going
makes
to
sense.
say right there.
This should be a minus, and this one down here should be a plus. So I'm going to say, I look at each transition, I look at all of the inputs, and I multiply them together. So here I'm going to get V times T. And then for every input place, I subtract that. And for every output place, I add that. So yeah, my signs here are precisely backwards. Okay. So this is what some people might call like mass action semantics. I'm saying every interaction it's governed by all of its input parameters and their product. And it sort of takes from the inputs and gives to the outputs.
Can I add a comment and maybe question as well? I
Hmm.
mean, clearly it seems as though when you have multiple inputs into a process, you by default multiply them.
Yeah.
Is there the thinking that some other interaction might happen? For example, I'm thinking with some exponents, maybe they're not one to one.
Exactly. Something interesting could happen here, and we are going to recover some of that behavior. And we're going to notice the classical thing that happens in mathematics, which is sort of the more constrained you are in the type of behavior you can describe, the easier it is to reason about those kinds of systems. So the more general we let this be, where I say like, oh, you could do anything, you could take their product and the sign of the powers of the things, the harder it would be to say something about that kind of system. So we're going to try to play the game of be as strict as possible and as concrete and like unflexible as possible, and only allow new kinds of behaviors once we see that we really kind of need them. That
Um,
way we're going to be, yeah.
Actually, I had something else in mind, but of course, what you said is a very useful thing to say in the context of modeling in general, whether we use this framework for representing the model or not. My question was intended to be more about the representation of the model. For example, what I have in mind is if we had a model in mind where it would be v squared times t, let's imagine, is there a way to represent it using this
Yeah, let's
formalism? So Do you see what I
Yeah.
mean? Like, so we can embed more connections
Sure.
and
So
get to higher powers that way.
there's sort of two answers to give to this. And one is there's a very interesting story that hopefully I'll have time to come to at the end between like I'll tell this whole story about the choices we made, and then at the end we'll go sort of like, what if we made other choices? Because we could have. What if I'd always wanted to have v squared t instead of something like this? And there's a very interesting story coming from sort of categorical database migration over here and ODE semantics. That's one story. Then here's the other story, which is, I think, the much more fun one, is like, yeah, sure, just put like a 2 on that arrow to mean I square it. That's perfectly fine. And there's something as category theorists we can do to make that work. So there's sort of a lot of.
Honestly, can I tell you what I thought? I
Yeah.
thought maybe you would, before where it says V, right? I can't point, like you don't see what
Yeah.
I'm pointing to, but where it says virus, you know, the V, you could put two of those and have
Sure.
another reaction that connects those two. So that's by default
Yeah.
V squared by your
Yeah.
rules, and
Or
then
I could
map
just
those,
take two viruses and put two arrows to infection.
or
There are
two.
lots of things I could do. Yeah,
Okay.
I could draw an arrow with a double edge. I could, something that's fun that a student once suggested to me is maybe the length of each arrow is proportional to the power that you do it in. So your diagram actually has like geometry. The longer the
Mhm.
arrow, the higher the power you raise that term to. So there's
Mhm.
lots of really interesting games you can play.
I'm only suggesting that it might be unnecessary, just in some cases, to add new syntax. Even with
Yeah,
the syntax you already have, you could make V squared by putting two copies of
exactly.
V and having them come
Exactly.
together.
And what we
That's
will
all.
learn actually from this very restricted syntax is what we're going to introduce, spoiler, is enough to describe arbitrary polynomial ordinary differential equations. So you can do everything with all this syntax. You don't need to add new stuff. But I really want to emphasize sort of the direction of this game really is, yeah, you want to end up with some new syntax? Do it. We'll find a way to interpret it. And that should be flexible. So anyway, all that aside, this is the rules we're going to play. We're going to play these sort of mass action semantics. I look at transitions. Each of these tell me how to modify my ODEs. I take the product of all of the inputs, subtract it from the inputs, add it to the outputs. So that's not quite good enough to get what I wanted. Because if I look back over here, I'll see that, yes, for v dot and t dot, I definitely have a minus vt term. And for I dot, I've got a plus vt term. But their coefficients are different. One has a beta, two of them have a beta prime. And it's not even the case that the two inputs have the same coefficient. They actually have different ones for each input. And if I go back to my big thing over here, I can see that beta is the rate of viral loss per target cell, whereas beta prime is the rate of conversion from target cells to infected cells per virion. So they're different things. They have different interpretations, different numbers. So let's just make up some new syntax. Let's say every time I draw an arrow, I'm going to label it with a real number or, a parameter that can be eventually substituted for a real number. And how do I interpret that? Well, when I still take the product of all of the inputs, but when I come to adding or subtracting that term to the ODE, I look at the number on the arrow and I use that as my coefficient. So let's just invent this as some new semantics we can play. So now down here, I've got a diagram where I've got a beta prime on this arrow and a beta down here. So when I look at the term for t, again, these signs are the wrong way around, you'll see that I use a beta prime when I'm doing the t1, and I use a beta when I'm building the equation for v. So here's some new syntax we can just make up. Great. This lets us recover 3 of the terms from this picture perfectly. And this picture circled in purple kind of looks like this picture down here. So it looks like we're kind of on the right track. So this is where I want to point out sort of like what we mean by making our assumptions explicit. So here's what I'm really saying when I draw this diagram is I'm saying, every time I see a process that I think deserves a name, like for example, infection, I'm going to say that gives me a specific monomial. Here it was v times t. And I'm also saying, but maybe its coefficients might be different, but each interaction corresponds to precisely one monomial. And these coefficients are specific to the input and the output. They're not just determined by the interaction itself. So I'm making a very strong claim, right? I'm saying every single interaction somehow just corresponds to a monomial. That's quite a strong claim to make, but I'm making that explicit. Um, and so for, yeah, people who've heard of this mass action semantics, you could say what I'm saying is I'm sort of doing mass action, but it's mass conserving up to a constant in one thing.
I think it might be worth pointing out to people who may have not thought about this before,
Hmm.
and I intend this from a categorical perspective, that an implicit assumption there, and in saying it's a monomial, it's not even just that it's a product or whatever. but that it's a monomorphism,
Yeah.
in the sense that when we have two things interacting to make one thing, the implicit assumption is that you get a unique thing out of those two things. There's
Yeah.
never two different, like possible
Yeah.
outcomes depending on some context or
Exactly.
history
So
or something like that.
this is a very like monomorphism. One thing. This another way of saying it is like this is a purely deterministic system. I'm not giving or nothing is parameterized. It's a very simple kind of guy, right? A process is a thing that always behaves the same and it does one thing,
And
and
in
that thing
particular,
is yeah,
that we've specified all the inputs. There's no context that is remains hidden. There's no,
exactly.
um, as I say, history dependence or something like that that has not been
Yeah, I
specified.
think that's the other thing to point down is sort of there's a very interesting thing, which again I would love to talk about, but I'm not going to. This sort of shift between modeling as I assume when I have a blank page that I am saying nothing, and therefore I have nothing, and every time I add something, I'm saying that's the only thing that exists. And you could call this a sort of additive view on modeling versus a subtractive view where I say, if I don't write down anything, everything could be happening. And every time I specify something, I'm sort of cutting down the space of possible things I could be describing. And this interplay between additive and subtractive modeling has some really cool interpretations in higher type theory and higher algebraic geometry and higher, like, it's very
And,
interesting. There's a lot of cool
and it
maths.
plays a role in quantum information as
Sure,
well. That,
exactly, yes.
but
So there's
that's
a lot
another
of
story.
yeah, I'm not going to get into any of it. Um, so let's start building up the diagram a bit more. So now I'm going to look at two more terms. So I'm not going to keep flicking back to the ODEs. I'm just going to promise you that there are these two terms also appear in the ODE. The V dot has at some point a minus mu VA term, and the A dot somewhere has a minus mu prime VA term. Okay, so V is our virus, A is our antibodies. So what is my understanding of this? I'm going to say, because I've read the parameter table and I've looked at the model and I still know nothing about biology, I'm going to say there's something called antibody virion binding going on. And what does that do? It takes some viruses and it takes some antibodies and it binds them together according to some equations. Now, if I draw this down here, you can see I've drawn this as a little hexagonal box and it's in gray. So this is still a transition, but I'm just noting that maybe it's helpful to note this transition has no output. It doesn't produce anything, it just uses stuff up. Okay, this just uses up some viruses and some antibodies and it binds them together. So something I'm saying here is I could give an output to this and call it like antibody virion bound guys. I don't know what those are called in biology, but I'm sure you get something when they bind. But what I'm saying, and I'm making quite explicit, is I don't care. I'm not keeping track of the number of them. I don't mind what happens to them. They are not part of my model. In my model, they bind and they disappear. They are no longer something that I care about. So something that you might see if you do sort of systems dynamic stuff or any of this like business modeling is there's this notion of clouds, they call them sometimes in stock flow diagrams, which is sort of this is a place where things go to vanish or where things just appear from would be the dual of these. One with no inputs, but just outputs.
Yeah, I
Yeah.
was gonna make I mean, I wanted earlier to make it and I got sidetracked, and then this makes me even more want to draw an analogy. But again, well, this could be very much an aside that you say, look, that's not really the time to talk about this. But this reminds me very much of diagrammatic modeling, which we've had a couple of
Mhm.
talks about, a few months ago
Yeah.
in this forum, and I know you're very interested in that. I mean, you're the one who introduced it to my students, and
Yeah.
but this would seem like interestingly in that context, like a measurement box, where it
Yeah.
almost feels as though you care about the measurement, but the point is you don't propagate the state. Then you lose the evolution that you wanted anymore. So it's as
Exactly.
though like you
Sometimes
didn't care.
yeah, I'm definitely not going to delve into this too much because that would take us off. But it's true. I'm just sort of saying, it's useful to draw this thing as a hexagon and make it a bit different because, I'm interested in as a process that's happening, an interaction, but in a different way. A lot of times we care about processes because we care about their outputs. But what I'm making very explicit, which is one of these sort of like little phrases that I love to hear said, is sort of it's a big fallacy to identify a process with the outputs of that process, right? This is something you'll hear a lot where, to give a maybe topical example, it's maybe true that I can use a computer to produce a large content of work for me, but it's sort of a fallacy to say that the output of having written a 10-page paper is the same as writing a 10-page paper, right? The process and the output of a process are distinct. So what
I,
I'm highlighting here in our notation is like, let's make that explicit. This green one is one where it's a process where we care about its output. This gray one is just a process that we care about because it's a process.
I feel compelled as a teacher to say that this is very relevant in the context of AI. And I find myself saying this to my students, very
Yeah,
often. So I smiled when you said it.
exactly.
For example, the paper or essay that you wrote or
Yep,
the solution you submit isn't the same as the process by which you did it. If you
exactly.
you know if you had an AI do it, then you didn't learn,
Yeah,
for
exactly.
example.
There's a big difference. So, yeah, it's important to note that sort of, yes, exactly. Don't conflate processes with the observables of a process. Might be, yeah, it's a cool quantum story here. I'm not going to get into it. But so this is what I mean by clouds, is we're going to have this notion of clouds. Sometimes we're going to have interactions that sort of don't produce anything, or they just spit out things for free. And these are sort of our like extremities of our model where we're not looking past those. So this other part here, I say no links. So let's understand what I mean by that. Here is another, on the left here, are another three terms from my set of ODEs that, again, by looking at the parameter table and looking at the diagram, I have sort of understood that these are sort of also involved in some process or some interaction. So you can see here, the way I've got these three equations back is with this little diagram here. So I have some I for infected cells, F for interferons, and so I have interferon production, which takes in 0 infected cells, but it still uses infected cells. So this is an interesting part of the notation where I can say, look, this corresponds to this term here, F dot plus equals QI. So if I want to express that in my diagram, well, I have to draw a box which has an I as an input and an F as an output because the monomial is I, so it needs to have an input I, and it has output F, so it has to have an output F. But if I look through my equations for I dot, nowhere do I find a minus I term. So somehow it's useful to be able to draw these boxes where something is an input, but it's really acting as like a catalyst in some sense, maybe, or analogous to a catalyst. It's not getting used up, it's just helping something happen. And we'll see the dual thing happen down here with interferons, or sort of the same thing, I guess, where if we look at this minus IF term, how will I get a minus IF term for I dot? Well, I'll have to draw a box which has I and F as an input. But again, if I look through my equations for F, they don't have a minus IF term. So I'm going to have to label another arrow with a 0 here coming out of interferons. So the thing that is sometimes common in this language of stock flow diagrams is this idea of a link.
Right.
So this is where I say that there is some flow, some transition, some process happening, and the rate at which it happens is parameterized by some other variable.
So the way I like to think about it, and correct me, maybe I'm wrong, and it's just an internalized sort of
Mm,
view of this. And as you say, it comes up all over the place in various different models, is almost as an instance of implicit scale choice, in
mm,
that, for example, it encodes some sort of signaling in this case, where the interferon sees that there is an infected cell and therefore
mm,
turns on the process.
mm,
But if I had chosen to model this at a lower or a finer level of resolution, like you said, with a catalyst, you could see a temporary binding where temporarily for a short period of time the
exactly.
catalyst is not available and then it gets released again. It's just that I'm modeling, I'm sort of not looking at that level of resolution and therefore just seeing it as a signaling that I don't look
Yeah,
inside.
exactly. So here I'm making sort of two statements which situate me along this sort of line of how I could be thinking about this. On one extreme is exactly this, like I should care that my catalysts get bound and are not available for a time. They do actually get used up at some time scale. So I'm sort of saying, well, I'm not peering in that much to the process. But on the other hand, what I'm saying is I don't have a new special notation like links would have in stock flow diagrams to say that, oh, this interaction down here is really just something that affects infected cells, but it's parameterized by the number of interferons. I'm just saying, well, to me, sort of parameterized rate is the same as a process that doesn't use up anything. I'm saying that, and I think I write this down. Here we go. I'm not distinguishing between parameterized rate interactions and zero consumption interactions. And that has a lot of impact. That means a lot of things. It means I will be making certain hypotheses about the actual biomechanics of my situation that are not true, right? But this is something I'm going to make as a sort of statement because I believe it to be useful for building this model. That
It's a
I won't
syntactic, it's a
distinguish.
syntactic choice, right? It simplifies, it smooths your syntax a little bit.
Yeah,
Yeah.
exactly. And it's also me sort of making it can be seen as sort of a negative and a positive thing. The negative is I'm saying like, listen, I don't have this level of granularity to distinguish between these two things. So in some way, my model's kind of like it's forgetting something important. But it's also a positive promise in that I am saying I promise you, my model is going to be independent of these two things. It doesn't matter whether these two things are actually the same or not, because I'm treating them as the same. So you won't be able to witness a difference. You won't be able to observe anything that's different between thinking about zero consumption or parameterized rate, because I'm conflating those ideas already.
I mean,
So yeah,
but that we do this in modeling. It has nothing to do with categorical modeling. In
exactly.
modeling, right, you have a layer of abstraction there, and you say, I
Yeah.
assume these two rates happen independently of
Yeah.
one another or something. Yeah.
Exactly. So the
Mhm.
key point to point out here is at the moment, it's very spurious that I've yet to do any categorical modeling at all. I'm just doing modeling. This is what modelers would call modeling. I've not done anything fancy and categorical here. And that's good. All the category theory should be sort of the best kind of applied category theory in my mind is that which is hidden and you don't really realize it's there and it's still happening anyway. So I want to look at like one last part of this big diagram before we start sticking it all together. And this is this idea of what am I drawing a box around and calling a process? So on the left here are three terms that come from the ODEs as well. And on the right here, I've drawn a way of a diagram that generates those three terms using the rules, right? There's some process, process one, that uses up delta infected cells to give me P viruses and Q interferons. Now, that is a diagram that produces those ODEs. But something I've been very sneaky about doing so far is I've pretended that at every step of the way, there's only a unique diagram that gives us these ODEs. That is not true at all. There are lots of choices of what we're deciding to be a process or not. For example, here, I can see there's actually three different diagrams which would give me exactly the same equations, right? I could say there's just one big process that turns infected cells into viruses and interferons. And maybe with what little I know about biology, I would believe that probably isn't a very good, accurate description. It might give me the same ODEs, but that doesn't sound true. I don't think cells turn into viruses and interferons. And then I could look at this second one, this option two, where infected cells just sort of disappear and they sort of, this dashed arrow is just my way of saying it's an arrow with a zero on it. So this one says infected cells just disappear but the presence of infected cells makes interferons and viruses appear. Um, and then this third one is even more granular. I say infected cells disappear, but the presence of them makes interferons appear. And also separately, the presence of infected cells makes the virus appear. Okay, so obviously using the word appear means I'm not doing very good biology here. But the key thing is, right, the reason these diagrams are so cool is that they don't just give you quantitative information. They give you qualitative information. And this is a real sort of reversal in mathematics. We're very used to it being sort of like the sort of narrative you're told quite often in these introduction to ODE modeling classes is, writing down the equations is the rigorous process, and the rest of it is sort of the informal process. But what we're seeing here is actually generating the right ODEs can be done in lots of ways. But I can be telling a very different story by sort of where I put my brackets, the way I notate this stuff, the way I sort of draw circles around different aspects, how I group up my terms. And this is the part where I think these tools are so interesting is this is a way of conveying information beyond just the ordinary differential equations. At the beginning of this, I just want to say, like at the beginning of this, we had this sort of order of like, here are the real ODEs, this is the real model, and here's an informal diagram. It's useful as an aid. But now we've flipped the script and we're saying this diagram contains all of the ODEs, but it also contains strictly more information. And that's the part that I find super cool, is that we can actually make these informal bits so rigorous and formal that they contain more information than merely the mathematical ODEs. They can contain information about the way we have partitioned and conceptualized the system in question.
I mean, they're what you said earlier, they are interrogable
Yeah.
or interrogable or how models. Um,
Yeah.
and so they go part of the way towards answering the question of why, which
Mm,
Eugenia Cheng often says is at the heart of, what mathematicians
exactly.
think about.
Yeah.
I mean, I think for teaching purposes as well as presentations, to focus, to sharpen the discernment between,
Mm,
if you looked at those diagrams, what different stories would you tell?
yeah.
What's
Exactly.
going on? Like the cells maybe die, the infected cells
Yeah.
die, but their presence, as you said, and there's further levels of detail, or there are two separate
Exactly.
processes that happen in different parts of the body,
Yeah.
let's say, that
Yeah.
create the interference,
Exactly.
and
And like, note here that I've drawn three of them. These aren't the only three. There are many,
yeah, there's
many more,
possibly
and
an
like,
infinite number of them
but like, yeah,
actually.
because the point to point out here, right, is I could sort of win this game trivially. I could say, look, here's a diagram. It's one single square. And the rules are whenever you see this square, you write down this system of ODEs. And I just tell you the system of ODEs in the paper. This is a formal, mathematically coherent object. This makes sense. This is a rigorous definition, but it's kind of useless. So here we're playing the game of like, not like sort of what is true and false or what is right and wrong. It's sort of like what is useful. What
Mm.
is the purpose of this? Maybe for the purposes I want this diagram to convey, actually the top story is good enough. Maybe this second one is more accurate, and maybe the third one is sort of more useful to pose questions to. Things have different utilities. There's different measures of utilities of a diagram, right? It's not just does it give me the right equations?
For the second time today, I'll mention the connection with AI. I think I
Mm,
would leave it to, it's kind of, I think, obvious to people what, your idea of the black box model that just gives the right
yeah,
answer. But
exactly.
yeah,
Exactly. Uh, so here's sort of another time I mean by like, what do I mean by this categorical modeling helps make your assumptions explicit is, we don't have to, if we see one monomial arise everywhere, so here it's the monomial I, we don't have to group every I term together into one single contribution. In fact, we're only going to do that when we want to sort of mean something by it, when we want to suggest that there's a good interpretation or understanding to be gained from doing that. That's a sort of another assumption we're making explicit. So now I want to do a brief little sidestep into where's all the category theory in this and sort of why, and then go back to doing this model. But it's only a very short part for now about the category theory. And I'm not even going to get into actually any rigorous category theory here. All I want to talk about is this seems kind of like a sad story where I'm saying, look, you've got loads of choices, you've got to pick one, and you have to tell me which one you picked, and that's it. That doesn't seem great because, as I've mentioned, these different choices could all be good in different contexts, right? So maybe what we're interested in is not just actually building one diagram to get this model, it's to study sort of like the diagram with a bunch of ifs on it. Like it's this diagram, but maybe if I did this instead, this bit would look a bit different. It's not just one diagram, it's a diagram along with sort of a list of all of the choices you did make and a list of all of the alternate choices you could have made. So the way we can sort of formalize this and the way that category theory starts to poke its head up from the under the water a little bit more is it suggests we shouldn't just study sort of like the set of all of these diagrams. We should just think of here's my diagram, it's done. We should understand the category of these diagrams. We should understand, okay, on the left, here's the choice I made. For example, I decided that in my diagram I wanted to pick this option three, but I could have picked option two instead. What would it look like if I had picked that option? How does my diagram relate to the other diagram? And we can formalize this in a very sort of dry, mathematical, rigorous category theory way by building a category of these diagrams and building morphisms between these different diagrams. This then lets us express these sort of conditions of, oh, here's my diagram, but had I made this choice, here is what the diagram could look like. And then anything you can ask me about my diagram, my claim is lots of things you want to ask me will be functorial. I can tell you what would have happened if I'd made these other choices. So this is where the one part where there really is some inarguable category theory going on, where I would call this categorical modeling, is because I'm not just doing the process of building one of these models, I'm understanding A, how do these models relate to one another? And B, why is it true that my queries that I ask of these models should respect this category structure I put on them? And both of those questions, the second one especially, are very much begging, like they really deserve a very strong answer for me to justify this. They deserve a lot of justification. Like the claim that any interesting question would be functorial is a big claim. There is a lot of justification to be done for that. But there is some justification. In fact, here's one claim is if the way you want to interrogate these models is by prescribing a system of ordinary differential equations to them in the way that I've been doing, and you then want to numerically simulate those guys, that is functorial, it turns out. Any prescription, if you wanted to come up with, so we'll go back to Ted's point here, if you wanted to come up with a different rule where, I know this isn't exactly what you said, but like you want to come up with a different rule where actually I don't take the product of the inputs, I take the product of one squared and the other one cubed, and then the third one to the power of one, and I come up with some different rule, and now I get some different equations, that is functorial. So this is not easy. It's not an immediate fact. In fact, like the story of, so what we might call like sort of migration for ODE semantics is very complex. It relies a lot of higher category theory, double category theory in particular. We've recently had a summer researcher, a student working with us on fleshing out the details for one specific example, and it is incredibly technical. Like this is not, I don't want this to be a story of like, oh, category theory says it's just functorial and you're done. It is a very hard category theory fact to sort of say even what functoriality means here. But the point is there is something that you can say, and this is the start of what we're using to actually implement some of this stuff in software. So
So
the yeah.
yes, thank you for saying this is I'm so glad we got to this point to say this. I mean I don't have much substantive stuff to say, but I just want to check my intuition here.
Mm,
Maybe others are following, but certainly in my mind, this point you were trying to make now, you were taking the perspective of it's very difficult to prove within the framework that we have that these are in fact factorial
mm,
properties and so on. But the way that I think about it is that this is more a sort of a linguistic question. In other
mm,
words, what framework we use to describe, like the language, the syntax that we choose to use, for example, in the context of ODEs, which
mm.
include all the possible questions I might ask of them.
Yeah.
I
Yeah. So,
choose to use
yeah.
that framework and whether that corresponds with a set of real world questions I have, like language questions. So it's a translation question.
Yeah.
I'm trying to, you know that I wanted you to talk more about that, and
Categorical
maybe in some
translation.
future
I
time
know.
we'll
Yeah.
get you to talk about that. But
Sure.
I feel
Yeah.
that that is the kind of question you're talking about
Yeah.
now, is a
I
translation
think,
question.
yeah, the key point I would make here is it's easy to be sort of like seduced by fancy maths and category theory stuff. I love category theory. I'm a category theorist in some sense of the word. But there's a way in which, like, for example, I could prove that ODE semantics is categorical trivially. I could just give everything a discrete categorical structure and I'm done. Saying that something is functorial in maths is a very interesting statement. But when I start talking about applications of mathematics, saying that something functorial might actually be entirely meaningless if that doesn't correspond to something in reality we care about. So the bigger claim here is, my justification itself needs a justification. I'm saying there is a category of these diagrams and there's a category of ordinary differential equations such that associating systems of ODEs to these diagrams is functorial. Great. But are those interesting categories and is the functor interesting? That's an even bigger claim now. What there are, and I mean, we went through a lot of them, there are lots of different ways of trying to build a category of ordinary differential equations. We've settled on one, which is through this, there's some fancy stuff about modal Cartesian double theories and multi-categories and symmetric list monads and lots of cool stuff. We've landed on one, but there's still a lot of onus to sort of show that this is a good one.
Hmm.
Definitions are cheap. Showing that those definitions are good is expensive, and that's where a lot of the hard work comes in a lot of this. The
Thank you.
maths is not easy, but there's another hard job, which is sort of justifying the mathematics. Yeah,
Thank you. Yeah, thank
cool.
you.
That's okay. So now, last thing I want to talk about in this specific model, because I'm aware that I'm also coming up to nearly speaking for 55 minutes, is brackets. So here are two equations which are entire, like, as a mathematician with a certain meaning of the word mathematician, these two equations are the same. If I were a certain kind of mathematician and I really cared about like linear logic, or maybe I cared about non-associative structures, there are ways in which these might not be the same. But, I think about ODEs, these are the same equations. I've just multiplied out this bracket to get the guy on the bottom. They're the same thing. But, the biologists, the mathematical biologists who wrote down these ODEs know that these two things are the same, right? And yet they chose, if you go back to system of ODEs, to write them in this top way. So there's something to be respected here, which is sort of like, that very well could have been a deliberate choice. Let's not just assume that this is a coincidence. And we can kind of see what this means if we try to draw both of these as diagrams. If we draw the top one as a diagram, what does it say? It sort of says we've got one process where maybe now I want to be able to label my arrow with not just a real number, but another variable, another parameter within my system, a state variable. And that now makes me, as a mathematician, I'm a bit worried. I'm fine with labeling things with real numbers. If I'm labeling things with other variables, I definitely need to rethink the way I'm understanding these things categorically. If I look at this second one, I'm much more comfortable because this says, look, there's two different guys going on, and I know how to draw two boxes and make the numbers line up. So this first one means something different because it's saying there's one process, right? Not two, but it definitely changes my mathematical story. So again, for the sake of time, I'm going to take the shortcut and I'm going to use this bottom one because it doesn't change the story I'm telling. But I want to point out that like this is like actually just this. There are two bits in this whole system of ODEs that were incredibly complicated and made me spend a lot of time on them. One of them was these brackets. The other one is a fraction that appears later, but these brackets have given me so much pause for thought. Sorry, I see Irfan's raised their hand. Is there a question?
Yeah, you might have already explained this, but what is suggesting that there's a minus sign in the second diagram for the
Uh,
M1?
the minus, so let's look at how this diagram works, right? So this says, I could have gotten a sign wrong here somewhere, but maybe not. So this says that like, here we go. So if you look at the B cells here, so this is an equation corresponding to B, and it has a plus term and a minus term. Minus terms occur whenever something is an input, and plus terms occur when it's an output. So you see here that B is an output of process X. So it's going to get a plus something term, and it will get a plus V term because this guy's input is V. But it's also the input to this process Y. So it will get a minus term, minus M1B. But actually, this process also has a V input, so it'll be minus M1VB. Does that make sense? So it's, places appear as inputs and outputs, and all of the places it appears as an output, it will gain positive terms, and all of the locations it appears as an input, it will gain a negative term. So my point is, this whole story just about this bracketing is an hour-long talk in and of itself. So it's not one for today, but I want to acknowledge that it's a big thing, and I'm actually going to skip over this one because I don't want to get into it. And this is what I mean by this is a whole talk for the future of what if I wanted to say, well, I picked this second one, but I don't like the fact that it has two boxes. I really just wanted it to have one box. Am I allowed to just black box it and stick it up into a little thing? And the answer is yes, but it's really hard. And it's surprisingly hard that this is the thing we struggle with. Really cool story, no time for it. So here is sort of our final diagram. So I'll zoom in a bit on it. So you can see this is much messier than the diagram that was presented at the beginning, right? So this is a much more complicated diagram. And in two places, you can see there are these little exclamation marks. These are the places where here I've done this trick where I've forgotten about the bracketing and I've decided not to worry about it. And up here, there's another problem that I haven't even talked about. So this is a diagram that perfectly recovers a system of ODEs that 90% looks like the ones in the paper. But it's a way worse diagram in some sense. This is not something that's anywhere, the first one was so snappy and short. It only had, I think, 6 bubbles and 9 arrows or something, whereas this guy's got loads. But there's a way in which I'm happy with this model, right? Like this model expresses how I have understood their model. The purpose of this is not to be like, oh, this is the picture they should have put in the paper instead. The purpose of this is for me to show it to Mary Lou and Nina and be like, hey, here's here's what I've understood. Is this right? And then they can point to it and go, actually, no, because like, why have you given this guy a separate thing? Or like, why is there no arrow from infected cells to B death? Those two things are related, right? So this is a really useful way of me conveying what I have understood. So here's the big model. And now I want to do a time check, actually. Could you just give me a rough guideline between 0 and 10 minutes, how much time I have left
If
so I
you
can
need 10, you can take 10.
okay, I
But
will try
between
not to
now,
take
yeah.
10.
Yeah, it's
Yeah, I will
okay.
try.
We're flexible. Yeah.
Okay, I'd just like to sort of, yeah, give answer my questions 4 and 5. So this here is sort of, I've gone through this process now. I've built what I'm calling a categorical model because I have a way of expressing what this model is using the language of symmetric nodal categories. I can talk about the way it recovers ODEs using a very specific double functor. I can sort of mathematically justify a lot of this story, and it's a useful tool for me to be able to show someone this and go, here's what I think this model is. Um, but here's where I want to talk about like at the very beginning, I said two big claims. I said categorical modeling is useful, and I still stand by that claim. And I hope that's something I've sort of justified here is like the purpose of it as an exploratory tool. And I can still get my ODEs out if I want to simulate them. But I also said it was difficult and complex. And then the second point was I said certain tools can make that easier. So I just want to talk about some really like down to earth ways in which this is complex. So here is, I mean, I wrote these slides, I drew this diagram, I drew it in my notebook lots of times, and it was an error-laden process, right? Like there are so many terms in the ODEs, so I circle them and then I draw some diagrams what I think does it, and then I like look at the diagram and generate the ODEs from it using my rules and check that it works. And then if I update my rules, I need to go back and recheck everything still works. And lots of times, you just draw an arrow between the wrong boxes, or your arrow goes in the wrong direction, or you've accidentally mixed up a beta and a beta prime, or you realize you've missed a term. It's very easy to not see an arrow coming in or to overcount something. Or something that I did that confused me for a long time is I've just made a typo and I spelled interferon wrong because it's a wrong word. And to the computer, if I tell it draw a diagram where the input is interferon and the output is interferon and they're spelt different, the computer will do what I've told it and generate two different things. Also, all of these diagrams, like this big one here, is written in a small little language called Mermaid, which just generates these as little HTML files. And you can see here, this is the Mermaid code that generates that entire thing. So it's quite readable. It says I've got 6 different boxes and some different round boxes, and then I got some hexagon boxes, and here are all the arrows between them. But you can also see how very easy it is to make a mistake here. If I accidentally put 1 dash instead of 2 dashes, or if I get this dot in the wrong place, or if I forget to close my quotation, all the things that just happen that are hard to do. So even when I come to check that what I've done is right, I often make mistakes when I try to turn these diagrams back into equations. And the whole point here is computers aren't good. Hot take is computers aren't actually that good at many things. They're good at 1 or 2 things. It's just that those 1 or 2 things are quite general. One thing computers are really good at doing is taking a set of instructions for turning A into B and then applying that to a specific A that you give it. So this is the part where we should be like, let's use a computer. So I just want to show super quickly. Here now is a diagram. This is the same as the diagram I just built in Mermaid, but it's in CatCollab, which is some of the software that we've been developing. It comes out of Evan Patterson's work on algebraic Julia, some of their early work with John Byers and Nate Osgood and Cheyenne Lee. Lots of people. I don't have time to go into all of this. But here is a little diagram, and here underneath are the equations that are generated from this diagram. The notation is different, but you can see how, like, I've got a diagram, it's got boxes and arrows just like before. Maybe I might want it to like look a bit more. Here we go. It's a bit more familiar now. And here are my equations down here. But what's interesting is this is generated from this notebook. So this thing here is the document that contains that diagram. And as you can see, I've written some words at the top. I've linked to the paper and I've said, here's the ways in which it's wrong. And I say, here are some things. I've got a place called T, V, I, and F, and here are all of my interactions. And here's all of my information. What's important to notice here is this thing here is not just like the Mermaid code where I type in random text. This thing here is what's called a structure editor. I don't just type in, T is a variable or T is a place. I click a box, I say I want a new thing called a place. It's broken because I'm not connected to the internet, so I'm not going to fix that. Sorry, I'm not connected to the backend. This is running locally for me. I can go in and I can edit any one of these. And if I check in here, sort of what will it let me type in? It gives me a drop-down menu. It's type checked. It says, are you giving me the correct things? And as I update this live, I could even bring up, sorry, yeah, I'm running this locally, so it's not working. But I could edit this thing live and see how my equations and my diagram edit live. So this categorical, rebuilding this thing in categorical is great because now I draw my diagram. It gives me little drop-down menus, and if I go back and I decide I want to change the name of A to like antibody or whatever, it'll update it everywhere. So I don't need to worry about any of this kind of stuff. And I can run all of these interrogations, like what are the ODE analyses I might want to run? Like, what does it look like to numerically simulate these? What if I picked a different choice of ODEs? What if I wanted this rule that every input is squared before I add it, or there are two types of places and some of them contribute quadratic terms or whatever? So this is sort of a very short story to this software side of things, which is what does it look like to build tools that support this process of building these categorical models? And that's sort of some of the concrete work we've been doing recently, which is, a whole nother talk in itself. But I would be remiss not to mention that. So one of the concrete outputs is I then spent a couple of weeks making it so that CatCollab had this capability to build these Petri nets, run this unbalanced mass action semantics, and generate these ODEs and show you the LaTeX equations and let you do this live editing from one to the other. And that would normally be a very hard thing to do. I am not a software engineer. But because of the way CatCollab is designed, which is based on a real sort of double categorical perspective on things, for people familiar with that kind of language, it's surprisingly natural to implement a lot of these things. So yeah, I'm not going to talk anymore about that, but I want to point out that there's lots of cool work being done on CatCollab at the moment and sort of how it's situated as a tool for support in these sort of model building exercises for models. And I think, yes, blank slide because I typed the word thank you as a little image and I've clearly forgotten to actually embed the image. But yeah, I'll stop there so as not to keep on going. But thank you all.
Thank you, Tim. That was fantastic. Thank you very much. Okay, let's see. Let's do this. Um, yeah, and I will remind people that Brendan Fong had talked to us, I think almost exactly a year ago, the end of August last year,
Mhm.
where he mentioned early development in Catco Lab, and it was sort of like the general idea of what they were planning to
Mhm.
do with it. And I'm so glad we followed up with this. And I can even imagine having another talk where, I'd love to see the difference this can make, for example, in a classroom. Like, how
Yeah,
can we learn to use it, even we being in the classroom? I mean,
yeah,
literally to do some
yeah.
collaborative, after
So
all,
I
it's
know that, yeah,
a
this is something.
lab, right? It's supposed to be
Yeah.
collaborative, so we could actually like build
I
some
think this is
models of
something
our own.
Nate Osgood's been working on with some of his students. But I've used this I gave a talk sort of similar to this at the university here with some students, and it's a great fun exercise to sort of live build these models together and be able to sort of, do this real-time querying of, oh, but what if this were this instead? What if the equations were generated in this ways? What if we changed the rules? And sort of this capability to do it on a shared, because Cat Collab's like, I don't know, like Google Docs, everyone can open the tab and it's live edited between lots of different people. The ability to sort of do this live and have the computer do the things computers are really good at, which is essentially bookkeeping. Having that capability is very cool. And I think especially in a sort of like education context, I mean,
Hmm.
some of our grant funding is specifically for CapCollab for sort of domain specialist use. Like, what does it look like if I really want to be good at building stock flow diagrams and their semantics? How is CapCollab a tool for this? But I think it's also very interesting to note that these same kind of tools are very useful for education and sort of communication, essentially, education as communication.
Hmm. Hmm.
Yeah.
Um, yeah. So I wonder, I assume this is available
Yes,
at
so I
this
would
point.
say the best thing to do is if you go onto the Topos Institute website, there's a bunch of blog posts about CatCollab. Writing good tutorials and introductions is work that we definitely still have to do. But there's quite a few blog posts. I've written a few. Evan's written a few. I think Kevin wrote one on CatCollab on the Topos Institute blog. There is also
Mhm.
just catcollab.org is the website. There's a bunch of example models in the help pages. There's a bunch of stuff you can play around with. We also have a Zulip chat for anybody who wants to sort of come in. It's quite a fun Zulip chat because it's it's sort of like a community chat where anyone can join and anyone can talk about, ask questions, talk about what they want, what they're using it for, kind of things. But it's also actually where we host all of our development chat. So that's
Hmm.
also precisely the place where the developers are talking to one another publicly about, sort of, I mean, it's an open source software project. So it's, you
Right.
know, it's kind of fun to be able to look at it, I would say.
Awesome. Thank you. Any other questions? Does anyone want to, chime in at this point? Grady, I know you had a comment in the chat. Would you like to talk about it?
If someone could read the question, it's really a question.
Right.
Or,
I'm happy to do that. So Grady, a few minutes ago, said models' imprecise expression of precise information is a critical strategic tool in educating the public regarding the errors and therefore dangers of science denialism, an epidemic in the Trump administration. Are there any initiatives to enhance models' heuristic value for the public?
Okay, so this is something that I definitely like defer to external expertise on, but definitely in the UK we see a growing amount of funding for this. I do believe this is becoming more and more valued. Is this idea of what might be called citizen science or participatory modeling or lots of these kind of things, where
Hmm.
you know it's it's not very surprising, I think, that yeah, I this is a very I get nervous talking about these things because you have to have very precise wordings to say some of these things. So, general caveat, I'm going to talk about this very loosely. But
Informally, yes.
informally, and there's lots of asterisks after everything I say. But in some sense, I think it's very easy to understand where science denialism comes from. I have a lot of sympathy for this. I really understand it that, if you look at something like a pandemic response where a government decides that there should be a lockdown, and if it feels to to people, right, that like this kind of came out of nowhere, it's for reasons that they tell us are true, but don't match up with what we're seeing in day to day. Why should I believe it? And if they tell me that it's true because science says so, and I think this is wrong, it seems like science is wrong. I can really have a lot of understanding behind where this comes from. So I think something that's really valuable is this process by which scientific research gets turned into public policy is something that is, should have public input, should be open to the public, should be publicly available. And, policies are somehow only as good as the people those policies constrain believe them to be.
Right.
A
The
stay-at-home
buy-in.
policy, yeah, a stay-at-home policy is useless if nobody's going to follow it. If you want people to follow it, like the most effective way, and there's a very oversimplification, is to get them to believe the reasons that you have for instituting that policy, right? Like if people believe it's a good policy, they will follow the policy. Like if they believe this is a genuinely productive thing. So all of these questions around sort of participatory modeling and citizen science sort of say, how can we better embed affected communities, sort of the people who are receiving this science from on high, into the very creation of the scientific act itself. And this is a beautiful topic that has ramifications far beyond just sort of like public policy, right? And again, I'll try not to get into it because it's very much not my specialty. But I think thinking about these tools, I'm not going to pretend CatCollab solves these kind of problems, but thinking about tools like this, I think is a really good first step. The ability to sort of sit down with people and do this process of, look, let's build a model diagrammatically, or just using some flowcharts or using some things. But being able to have that as a mathematically formal object, I think is a very empowering thing. I think something we can see a lot is, you might go to your local town hall to say something, and it's very easy to be like, oh, they're planning to build a new data center here. I don't like that. But if all you as a citizen can say is like, I don't like it, I think it will be bad, but what, a large corporation has is a bunch of graphs and statistics and things go, no, 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 look in all the ways this will be good. There's a real power imbalance there. So I think one of the things that this sort of citizen science and participatory modeling can bring is sort of empowering people to sort of force respect upon their decisions by going, look, you want something mathematically formal? Fine. It shouldn't be the case that we have to mathematically formalize everything for it to be treated on the same footing. But if that's the game that is going to be played, let's build tools to empower people to sort of shrink that barrier between these sort of like wavy, fuzzy, qualitative opinion arguments and quantitative ones. So
Mhm.
trying to find ways to sort of So a phrase I've been thinking about a lot recently. I was speaking with someone this morning, Laura Accion, about the idea of mathematics as a humanities subject. And I think this kind of stuff is
We
precisely
talk about
within.
that a lot actually here.
Yeah,
Yes.
exactly. So I know this is a very sort of like sympathetic audience to that, so I don't want
Yeah.
to preach to the choir. But I think, yeah, a lot of these questions comes back to sort of how can we reinforce that mathematics truly is a humanities subject? And I mean, in some sense, the whole science humanities distinction is artificial, but sometimes distinctions are useful, even if they are artificial. Whatever, whole complex story. But again, to sort of be blunt about it, I think this all feeds into the story of like, what about mathematics as a humanities subject? And I think these kind of questions are sort of at the core of the way we are thinking about a lot of the work we're doing here around scientific modeling. So, I don't have a good concrete story yet about like, our plan is to use CatColab to do X, Y, and Z, and this will release the things. But I think even being able to sort of situate research around these kind of questions changes the kind of questions you ask and the way that you critically evaluate success of your projects, right? So this is what, yeah, part of my job now that I'm social impact lead is sort of like, what does it mean to bring that kind of thinking to these research projects? And that is a lot of learning on my behalf to sort of understand what this means, because there's a lot of people doing it very well, but not often within mathematics, because yes, I'm not going to carry on this digression because it'll go on a long way. But yeah,
No,
basically,
Tim, you're
yeah,
perfectly fine to do that. And I think I
sure,
can see Grady is very pleased with
sure.
this.
No, I'm just, yeah, I'm aware it was a short question and I'm now turning this into a monologue. But yeah, in short, I don't know if I've answered the question or not, but like, yes,
You,
good question. And I hope, yeah.
you've more than answered it. The impetus behind my question is generally described as how mathematics, as I've discovered it, being a member of this group for now over a year, and having just taken Algebra 2 in high school,
Mm.
I, I leave every discussion with a vivid sense of how mathematicians, like the members in the group, yourself, uh, in part because of who you are as a person and how you convey that, and also what you say about how you relate your life and life in general to math, which is what you're talking about. So you've answered my question when you said that you had not come up with a particular initiative or activity, but that you very humbly understood it as something you want to uh, learn about and to know how to present it as an objective in the mathematical research process. Because the way I look at the way math and mathematicians in this group relate themselves to the problems and challenges of life is that it was presented to me as a compassionate application of mathematics. And when I looked at it that way as an outward-looking humanities mathematics kind of approach, I contrasted that with, and this is not down-putting the persons I'm going to talk about in the math community, but there are impassionate mathematicians and compassionate mathematicians. The impassionate mathematicans are those who think, for the most part, within professional academic terms. And they look at academics as something in and of itself. They would not argue with you about applying it, but that's not their primary focus. So when you talked about your vision of bringing this broader perspective to the list of objectives for the agenda, you've answered my question.
That's great.
There is that spirit abroad and in an area where I think the general public is so unaware of how everyday people, mathematicians are,
Yeah.
and how much you struggle and you're humble. And that portrait of mathematicians has been drawn for me over the course of the last 18 months that I've been coming to these discussions, sort of listening in, trying to pick up what I can. But what I get at the end of every visit is a spirit that you have about you and how you use your mind and your intelligence to do your job, like we all do, and also to make the world better. So you have answered my question. Thank you.
That's great. Thanks. That's really lovely. And I will just say, yeah, I think the thing that I really want to point out is like, yes, work going on in participatory modeling and citizen science is like incredible. And I mean, it would be great to hear someone from that kind of area talk at this seminar, I think is what we're hearing. But I want to point out that like, yeah, this is not my expertise. And I really think there's a wealth of information there that I still have yet to learn from. And I think a lot of us have yet to learn from. Yeah, sure.
I think something you said earlier, I want to connect with during the talk, you said this, which is moving away from essentially, and I'm generalizing a little bit from what you said, but
Mm,
moving away from construing the world as a set of facts, as a set of answers or products, and thinking about it in terms of questions, in other words, processes. And
mm,
I have in mind, you probably can recognize, and this is very deliberate too, a sort of a categorical lift, if you will, from thinking about it, the set of knowledge, math or whatever, or epidemiology, as sets, because
mm,
in a set theoretic view of the world, things just are. They are either right or wrong. They can just be only, and they pre-exist before you ask about them, right? Their attribute exists.
mm,
But to think of them as processes, which means they have inputs and outputs. They're ifms, as
mm,
as Philip Ball says, which we use, for example, in modeling quantum systems, right? But it's broader than that. It is more a view of, of knowledge of any domain that is more categorical, that allows
mm,
these if-then statements, these contingencies,
mm,
which in some way, I mean, it's not just one step. Once you take that step, it becomes an infinite ladder of steps, like we see in category theory, right? It embeds itself.
mm,
And if you embrace that, it is naturally inviting to more people. It doesn't close off. It doesn't say this is it, this is the answer, this is the way, right? It's compassionate, kind of
mm,
automatically by default. And so I feel there's something important there that goes far beyond how we're gonna answer the next pandemic or how
mm.
we teach math in the classroom. And it's just a different,
Yeah,
epistemology, let's say, about the
yeah.
world, right?
I definitely think, yeah, most of my, yeah, the real thing I think I come to realize these days is most of my views on mathematics and lots of things come from sort of two facts or like two facets of my life, right? And one of them is like, even it's quite funny. So I work in an office full of category theorists, and I did my PhD in sort of the interface of category theory and higher geometry. So I've always believed that I was somewhat of a category theorist. But what I've started to realize recently is saying that like you have a sort of categorical view on things is, how what category theory were you raised on? I am told very frequently in this office that like, I think like a geometer in some senses. And like even the way I understand category theory is through geometry in some lenses. So, but one thing is like, you know, if you spend 10 or 15 years researching a subject, it will just give you a very specific sharp lens, and you will get very good at sort of understanding that lens and the way in which it frames things for you, and you'll get very good at looking at things through that lens, right? And if you talk to enough people with different lenses, you'll start to realize how very specifically shaped your lens is. But one thing that really shapes my view of maths is, like the specific mathematical upbringing I've sort of had. But the other thing that for me is like really behind all of these conversations, apart from like recognizing sort of the amount of mathematics that has been sort of drilled into me, so it fundamentally changes the way I view the world, is just like how much sheer joy I had as a child from like learning mathematics, seeing it as a thing and being like, wow, aren't these patterns cool? Isn't this thing cool or whatever? And I think a lot of, I know I hear you guys talk about compassionate mathematics, and my sort of, for me, this is, not in a pejorative way, but I see it as sort of downstream of mathematics as like a thing that I just love in many ways. Like the activity itself is something that brings me a lot of joy. And even when I start thinking about this sort of, what does citizen science or participatory modeling look like? Honestly, part of that is I find it exciting because like I would love to talk to people about maths and sort of like get them back excited about it. So there's always this sort of educational aspect in I think a lot of this sort of applied mathematics work, right? Is like applied mathematics is only as good as you can communicate it to be good. And, again, a very reductive phrasing would be sort of like education is communication. Education is good communication in some sense, right? Like to a very specific audience with a very specific target. But yeah, so I think all of these stories about sort of like compassion, education, knowledge, all of this stuff for me is like one big lovely little lump bundle that's really nice to look at all of the time.
Well, thank you again, Tim. It's so nice that you were able to take the time to do this
Oh, thanks
and
for
to
having
connect
me.
us with, colleagues at Oxford. It's close to my heart, as you know, and I can't wait until the next time I can visit. But we'll continue the conversation, certainly, behind the scenes, and especially as your time is more available. You have more time
Definitely.
to devote to this.
Mhm.
There's a few ideas that were floated, so we'll close out. But
Great.
thank you and good luck with your
Thank
efforts.
you all. Thank you all. Okay. Yes. Thank you. Yes, I got to run to another meeting. So
Of course.
thank you all. Okay.
Bye-bye.
Bye.
I just ended the stream. We can chat if we want.